Well, uh, we studied this one. Hello, I'm audible. Is the screen visible to you?
Yeah,
Yes, sir.
yes,
Yes,
sir.
sir.
Yes, sir.
Okay, that's correct. What is visible? By the way, what is visible?
Sir, 12th January 2021 class.
Acha, that white screen that is visible, whiteboard that is
Yes, sir.
visible. Okay. So, given a vector A and another vector B, which are not orthogonal to each other, we tried to find out the projection of one of the vectors, let us say B, projection of B onto the line A. This is what we tried to find out. And here in this regard, we got something called P. This is the P vector. And this P vector, along with this P vector, we got from this C vector. C is equal to B minus P, or P plus C is equal to B in that way. So this red color, that is the orthogonal part. And if I start it from here, this is again from the origin itself. A is orthogonal to this C and so on. So we got this vector P, projection of B onto A is P. P is equal to x cap A, and this is what we got as P is equal to A transpose B upon A transpose A times A. So this is what actually we got, and we later on manipulated it to a projection matrix. And instead of putting A outside, we brought A inside and took B outside, so that the entire matrix, entire numerator and denominator would comprise of comprising A only. So A transpose upon A transpose A is something we call it as a projection matrix times the B vector that gives us the projection P. Projection P is projection of the vector B onto A is equal to P matrix, projection matrix times B vector. Okay, so think of a scenario. Think of a scenario. You are given a set of vectors. Let us say the vectors are v1, v2, vn. They are the vectors that are given, and these are the non-orthogonal basis vectors. And you are asked to find orthonormal basis vector out of these vectors. So what are the steps that are to be done? And the steps are usually uh, known as Gram-Schmidt process. SCHMIDT. Okay. Gram-Schmidt process. This is very simple one actually. If you see, the target is to get orthonormal. Orthonormal. So first let us get orthogonal, then we can convert it to orthonormal. So obviously the step one is to get orthogonal vectors, and step 2 is convert to orthonormal. Step 1, let us say. So let us say the orthonormal vectors for these non-orthogonal vectors v1, v2, vn. Okay, for the set um, okay, so for the set non-orthogonal vectors v1, v2, vn, let us assume that u1, the corresponding vectors, u1, u2, un are the orthonormal vectors. Okay, actually these are the things we have to find out. We need to find out u1, u2, un in terms of v1, v2, vn, and so on. So the very first step in step 1 is take any one vector as a part of the orthonormal vectors. Let me start from the first one. So let us take u1 is equal to v1. Okay, u1 is equal to v1. Then we will find out what is u2. u2 is equal to how much? Obviously, v1 and v2 are not orthogonal. However, u1 and u2 has to be orthogonal. So u1 I have taken as one of the basis vectors. So what should be the um, what should be the uh, what should be the u2? What should be the vector u2 so that it will be orthogonal to u1? For this, let me get back to the previous class. As I told you in the last class, this is the basis for the next class. Let me take you to the previous class where you can find, okay, this vector A, let me call it as u1. This vector B, let me call it as vector v1. This is u, let me write it here. No, it will be better if I do it here. Just a second. Let me, yeah, let me put it here itself. This will be better. Okay. So I have one vector this is my V1. I have another vector. This is my V2. As per my steps, what I have done, I have taken this vector V1, U1 is equal to V1. This is what I have written. So this is my U1 vector. Okay. Now I need to find V2. I need to find U2 in terms of V2. So what I'll do here, I'll go for a projection. This is what we have done in the last class. And this projection is nothing but this is, if I say E, and this is P. So E plus P is equal to V2. Okay. This is what we have done. Now this projection U2, now what is this U2 is actually? U2 is nothing but this E plus P is equal to V2. This E is nothing but U2. So what is U2? U2 is equal to V2 minus P. What is P? We have already seen in the last class. What is P? P is equal to X cap A. P is equal to, where the close. P is equal to X cap A. This is what we saw in the last class, right? What was X cap? A transpose B upon A transpose A. Times A. Now the same thing if I put here, what is P here in this case? U1 transpose V2 upon U1 transpose U1 times U1. Yeah, that's it. Now can you correlate these two? Are they orthogonal to each other, U1 and U2? Just check this, whether U1, U2 are orthogonal to each other. If they are orthogonal, U1 transpose U2 becomes, I am pre-multiplying U1 transpose with U2. That is what I am doing here. So U1 transpose V2 minus U1 transpose minus u1 transpose u1 transpose v2 upon u1 transpose u1 times u1. So this is equal to 0. So u1 and u2 are orthogonal to each other. Now for two vectors we have found, for v1 and for v2. What about u3? u3 has to be derived in such a way that u3 is orthogonal to u2 as well as orthogonal to u1. That's right. So what exactly here we are doing? Here we are taking the second vector. We are assuming the first vector, the part of the orthonormal. It's not yet orthonormal, huh? This is still orthogonal. We are in the step 1. We are still in step 1. This step. We're still in step 1. Step 2 we haven't gone. So let us first complete step 1. So what exactly we have done in case of u1, we have assumed v1 as a part of the orthogonal set. And the second thing that we did in case of u2 is use this plot, this drawing, and find out that what is u2, and this I referred it from the previous class. And more precisely, if you see, u2 is actually the original basis vector, non-orthogonal basis vector v2 minus some term, v2 minus something. Yeah, that something is, we derive it from like this, e plus p equal to v2, and that is what we did here. Now u3 has to be found out in similar fashion, that is v3 minus some term that is related to u1 and some term that is related to u2. Then only we can find out u3. So u3 is equal to v3 minus let us say, yeah, u1 transpose v3 u1 transpose u1 times u1 minus u1 no, not u1, u2 transpose v3 u2 transpose u2 u2. So that's it. So u1 is equal to v1, u2 equal to v2 minus u1 transpose v2 upon u1 transpose u1 times u1. u3 is equal to v3 minus something from u1 and something from u2. Okay. In that way, if we go on, we can find out what is un is, and this completes your step 1. Now what is step 2? Step 2 is normalize each of them, each of these u1, u2, un, you need to normalize them. What is the way to normalize? Divide it by its length. Divide it by its length. So u1 is equal to, what is the length formula? Length formula is u1 transpose u1 square root. Similarly, u2 is equal to u2 transpose u2 u2. So in that way you can find out what is un is. Un is equal to un upon un transpose un. So now you have the set of orthonormal vectors u1, u2 up to un obtained from a set of non-orthogonal basis vectors v1, v2, vn. What is important to be noted here? The span of u1, u2 and the span of v1, v2 are the same. The span of are the same. How are they same? How are they same? Just look at this. u1 is equal to v1. u2 is equal to u2 is equal to v2 minus something times v2, right? Is this not a linear combination of v2? u1 is equal to v1, u2 is equal to v2 minus something times v2. Is this not a linear combination of v2? Similarly, u3, is this not a linear combination of v3? Right? This is just a linear combination of v3. u1, u2, u3 up to un, these are all the linear combinations of their counterparts v1, v2, v3, vn. So what we saw in the very first class, if the span of v1, v2 are given, if something is the, sorry, if something is the span of v1, v2, vn, their linear combination is also holds the same span. So the span of u1, u2 up to un is nothing but the span of v1, v2 up to vn. u1, u2 are no more than a linear combination of v1, v2. But the important thing is u1, u2, un are all orthonormal basis vectors, whereas v1, v2 are not. Okay. So for example, I have v1, v2 is equal to 0, 1, 1, 1, 1, 1. This is my v1, this is my v2. Okay. Can you find out what is u1, u2? Obviously, u1 would be 0, 1, 1, and what is u2? u2 is equal to v2 minus u1 transpose v2 upon u1 transpose u1 u1. This I can write it as u2 is equal to v2 1, 1, 1 minus u1 transpose 0, 1, 1 v2 1, 1, 1 u1 transpose is 0, 1, 1 0, 1, 1. This is multiplied by 0, 1, 1. Okay. Find this out, how much it is. One, 1 minus 0, 1, 1 times row times column, row times column. That is nothing but a single value, a scalar quantity. So this is 0 times 1 is 0, 1 times 1 is 1, 1 times 1 is 1. So upon 1 is the numerator is 2. And the denominator is, it's again 2. Two by 2 is equal to 1, 0, 1, 1. So this becomes 1 minus 2 by 2 becomes 1. 1 times this becomes the same vector. So 1 minus 0 becomes 1. 1 minus 1 becomes 0. 1 minus 1 becomes 0. This is u2. Okay. So now normalize it. u1 is equal to u1 is equal to u1 upon u1 transpose u1 square root, which is equal to 0, 1, 1, and U1 transpose U1 square root is how much? 0, 1, 1, 0, 1, 1. This becomes 1 by root 2. So this is your U1 is. Similarly, U2 is U2 so this becomes U2 transpose U2, U2 is 1, 0, 0. So this becomes 1. U2 remains the same. This, by seeing this itself, you can say that it is an unit vector 1, 0, 0 along the x-axis. So it remains the same 1, 0, 0. Okay. So this is one vector, and the second vector is, this is U2, and the second vector U1. U1 is 0, 1, 1. 1, 1, somewhere here in this. This will be 90 degree. Yeah, that's it. Gram-Schmidt process. So, anything you have to ask regarding this Gram-Schmidt process? It's a simple one, right? It's not that complicated. Yeah, of course, considering the fact that this part is understood. The previous class is understood. This class is a cakewalk. Okay, that's all for today. See you tomorrow. Thank you.